In this video, we're going to cover section 8.7 on halogenation. So halogenation is the last addition reaction that we'll look at in this section. And halogenation involves the addition of diatomic halogen across an alkene. So that's normally bromine as Br2 or chlorine as Cl2. So halogenation occurs in a way that places the two halogen atoms on opposite sides of the pi bond. So this mode of addition is not syn addition like we saw with catalytic hydrogenation and in hydroboration oxidation, but this mode of addition is referred to as anti-addition. So as you can see in this example, we have cyclopentene reacting with bromine, Br2, and what we observe is the formation of two products. And these two products are mirror images of each other. They're two possible enantiomers from this reaction. Now note that this bromine is coming towards us or above the surface of the screen, whereas this bromine is below. These bromines are not on the same side of the ring system. This is the anti-addition result. And you can see that the other enantiomer, the same situation, same scenario. We have one bromine that's below the plane and one bromine above the plane. So when we have two chiral centers formed, and these are the two chiral centers in each of those structures, we only observe two of the possible four enantiomers. We do not observe the dibromoalkane or cycloalkane in which two bromines are on the same side of the ring system. In both cases, these bromines are trans with respect to each other. They are on either side of the plane. So the requirement for anti-addition determines which pair of enantiomers is produced. And it's always going to be the pair in which you have the two halogens on either side of that plane. So let's look mechanistically at why this is what we observe. And before looking at the specific reaction, we should say something about these diatomics, bromine and chlorine. Now, molecular bromine, Br2, this is a nonpolar compound. However, it is polarizable. So Br2 is polarizable, and remember that polarizability in a sense is the ability of the electrons in the valence shell around these atomic centers to be interacted with or sensitive to their environment. So if a nucleophile is approaching Br2, there's going to be a temporary dipole induced as a result of that interaction. And so as this nucleophile is approaching this diatomic Br2, we see a delocalization in a sense, or polarization is more accurate, polarization of the electron density in this particular molecule. You see there's a shift of electron density towards the opposite end of this molecule, whereas the bromine closest to the nucleophile will experience this partial positive charge. And so the nucleophile in this example, in this section, is the alkene. And so as the electron density of the alkene approaches Br2, there's going to be this induced dipole moment in Br2 such that we have this partially positive end of the molecule which will accept that electron density, and the other end, being the more electronegative part of the molecule, will also accept that original bonding pair. So let's look at the specifics of this addition reaction in which a halogen interacts with the alkene. And so when a halogen, like Br2, interacts with an alkene, we observe, as we mentioned, anti-addition. So if there were, let's say, this particular scenario, let's say there were a carbocation produced, and if that were the case, we would expect that the bromide that's resulting after this step could attack in a nucleophilic manner from either side of the ring. So we would expect that syn and antiproducts could form. But as we saw in the previous example, we only observe the products resulting from anti-addition. So this mechanism isn't accurate. This is not the mechanism that would describe halogenation of alkenes. So let's see what mechanism we have proposed that tends to explain the observed stereochemistry. So halogenation does not involve the formation of a carbocation. Similar to oxymercration, we see a bridged intermediate forming, and we refer to this as the bromonium ion. So you can see that we have an alkene interacting with Br2, so we have the electrons from the pi bond attacking in a nucleophilic manner one of the bromine atoms. As that's happening, electrons from the bromine atom are going in two directions. There's a pair that will form an interaction with the other carbon of that alkene, and at the same time, the bromine-bromine covalent bond is breaking. So there's two concerted steps happening here. There's two steps occurring at the same time. We have nucleophilic attack and loss of the leaving group, and at the same time, we have electron density from the bromine atom that was attacked interacting with one of the carbons of the original alkene. And so we form this cyclic intermediate referred to as the bromonium ion. So it's this triangular, this three-centered intermediate where the bromine is bridging both carbon atoms of that original alkene. And this is proposed to be the mechanism for halogenation. And this helps us to understand why we don't observe syn addition. Why is that the case? Well, now when the bromine atom is trying or is attacking the bromonium ion, it's only going to do so from one side of that ring system. It can't approach and attack either carbon of that original alkene because they're bridging this particular bromine atom. And so as a result of this cyclic intermediate, it in a sense protects this side of that ring system. So the bromide really only has an opportunity for nucleophilic attack from the opposite side from which the other bromine has added. So in the last step, we have nucleophilic attack, and it doesn't really, in most cases, depend. In this example, it doesn't really matter which carbon atom is attacked. If there was a substituent, you could imagine that you would have greater nucleophilic attack on the less sterically hindered carbon atom. But in this case, either will be attacked, and what you'll end up with is the dibromocycloalkane. Now, because you could have attack here or here, this gives us that pair of enantiomers. So the bromine attacking here will give you one enantiomer. So we have a nucleophilic attack, and we break the carbon-bromine bond of the bromonium ion to give us the two dibromocyclopentane. But if the bromine atom was to attack at this position, we'd end up with the other enantiomer. So this mechanistic proposal explains why we only observe 2 of the 4 possible enantiomers when 2 chirality centers are present in your product. So the same mechanism applies for chlorine. Chlorine and bromine are by far the most common reagents used in halogenation. So this mechanism is testable, is one that you should be familiar with. And if you have any questions about it, any questions about halogenation, by all means, send me an email. Thank you.